Thank you for reminding me there, Isabella. Okay, so how to rotate dienes or really any kind of conjugated alkene that can go through a cycloaddition. Okay, so essentially what you're trying to do, right, is the reason why it's called S-cis, S-trans, right, is it refers to the axis of the sigma bond, right? So the kind of main sigma bond that you have that you're looking at is this in between dienes or the alkenes, right? I'm not sure if the terminology is used for trienes, but I mean, it still kind of applies. Actually, no, it is, because then you have two S-cises technically. So anyways, what you're trying to do is essentially you're trying to rotate this group on the same side, right? So if you consider this bond as like the S-axis, right? Right now, along this axis, they're trans to each other, right? So all you have to do is kind of, so a lot easier with or molecular model kits or whatever. Then I would have just turned on my video and literally rotated them. But I don't have any. But if you come in on campus or whatever, Professor Kovac has a bunch that he always lets me use, so I could always show stuff using that. Anyway, so you're rotating one group, this blue group, along that axis, right? So essentially it was pointing this way right now, right? We have the bond still kind of at the same thing, right? And this group was kind of going in that up direction. Now it's going in the down direction, right? So it doesn't matter what kind of groups you might have here, any sort of electron donating groups, right? When they're pointing up, right, like this, they would be technically outer groups, and then if they're pointing in, they'd be inner groups, right? So let's call this EDG1. This would be EDG2, right? And EDG1, second, rotate it. Actually, we'll end up here. Yeah, I'll have to check examples of that, but I'm pretty sure once you rotate it, it should be pushing inwards, and then
Can I ask something real quick?
Yeah.
Well, what exactly makes it an electron donating group, and what makes something like an electron withdrawing group?
Okay, good question there. Let me get into that in a second. Let me just show you how to rotate this one as well, right? So this one, the two x-axes are these kind of, right? So you're basically trying to have this bond be cis to the N bond, right? So then if you rotate this way, right? So this is the original one on the side here. The other double bond remains the same. It's kind of pushing inwards, and now the other one is this. So now this is the S-cis form for 135 hexatriene. I think that's what it's called. So yeah, I mean, so if you got a question with the S-trans one, I mean, you could probably ask him in this lecture. But like technically, if it's drawn as S-trans, you could say there's no reaction that's going to occur. You have to change it to the S-cis form. But like if he gives you a question with like, the butadiene drawn out like this, plus like, I don't know, something like this, right? Ask him if like he would accept no reaction for that, because technically this is S-trans, right? But if you want to make sure you just get it right, just show on your exam that you changed it to S-cis. Oh, whoops. And then go forward with the deals holder. He said to always rotate it. Okay, yeah, because I know Professor Andia technically that was on one of his exams where he'd accept both, right? Like you could, change it to S-cis, rotate it and do the reaction, or you could just say it's no reaction based off its current configuration. Okay, so that was somebody asked there about the electron donating and withdrawing groups, right? So we kind of briefly talked about this.
Before you go to that, can you just explain the last problem? I don't get that. The addition of the the second structure makes the S cis. Yeah.
Yeah, so you always have to, right now it's in the S transform for Diels-Alder's reaction to work, right? They have to be in the S cis form. So that just requires a small barrier of energy, right? So when you just put a little bit of energy in your reaction vessel, like by heating it up or whatever, right? You're gonna see this bond rotate, like the rotation we did, right? And then Diels-Alder's reaction specifically, 4+2 additions, they always happen. They have to be in this form. It has to be S cis always, right? You can't have a reaction without S cis, right? Because it puts strain on this molecule, increases the energy of it, right? And allows it to occur basically, right? Yeah, so diene is a good HOMO, dienophile is a good LUMO, EDG, electron withdrawing groups. Well, generally for those, that's what you'll see, but EDG and electron withdrawing, like EDGs and EWGs can be on any sorts of molecules. You're gonna see this a lot in chapter 18, which is when they first introduce it. But essentially, let's say we have, I don't even know, we'll do 2 examples, right? Let's say we have an alkene, right? And we put a OH on it, right? We have a phenyl ring, right? We'll put, I don't know, we'll put OET on it, right? Then we have, let's say, to make things a little bit similar, put something like a, acyl chlorides would be good. I'll just leave it as an acetate group. That's fine. Another example would be something like a nitro group. Right, and I forgot to draw the phenyl part of this, and then you have this, and you have this, right? So kind of the thing with electron donating and withdrawing groups, right, is all about what they're doing in terms of electron density, right? So on the examples here, on the left-hand side, let's start with the vinyl alcohol there, right? Remember, oxygen has lone pairs on it, right? So this is somebody asked this yesterday, and it's kind of hopefully clarified it up for them. But you guys have been taught, like, you know, when you have an oxygen carbon bond, it's very polar. That's true. You guys just saw that in ethers, right? When you have this, these are going to be technically partially positive. This is partially negative, right? There's an electronegative difference. It's a very polarized bond, right? But those effects are all inductive effects, right? It's just that, you know, it's based off, you know, the nucleus of oxygen wanting more electrons, right? It's not a full on, like, you know, lone pair donation or resonance, right? It's just inductive effects, right? That oxygen is withdrawing electron density. It's not like a full on movement of electrons, right? So here, when you have something like, you know, any lone pair next to a pi bond, right? It's going to be donating electron density into it, right? And this is just one example of it. Like here, let me pull up the full table. So if you guys want, this has all the examples. Table 18.1, right? And you're gonna see this in that entire section, right? It's basically electron donating groups are groups that can, you know, donate electron density, whether it's through a lone pair or hyperconjugation, which we'll get into in a second as well. So in this case, you have lone pairs that are allylic to a pi bond, right? So despite the, exactly, through resonance, right? So despite, you know, the oxygen carbon bond, right? The lone pair would rather resonate than, you know, oxygen pulling electrons, right? So then this would kind of push up this way and you get like a resonance structure that would look like this, right? Right, and now you could see that where the alkene was, there's electron density there, right? Because those lone pairs move there, right? And that's what means by electron donating, right? It's something that could push electron density to somewhere else. So whenever you see, you know, alkenes or phenyl groups that have like, you know, substituents that have a lone pair directly next to them, right? Those lone pairs can resonate with them and push electron density into those, you know, alkenes or the phenyl group. Same thing over here, right? You're gonna see this lone pair push in there, right? I guess we could do this a couple of ways. I'll draw the ortho example, right? And draw this here. Now you have a double bond here, right? Now you see this phenyl ring, right? Yeah, we broke aromaticity, but don't really worry about that. Now it's more electron rich, right? Because that group can push electron density into it, right? And what you're going to learn in chapter 18 is this is extremely important for you know, the real process behind electrophilic aromatic substitution, right? Is these are called activating groups, right? Because they're pushing electron density into the ring, right? And the ring acts as a nucleophile in all those reactions. So if the nucleophile is more electron rich, it's going to be more likely to do reactions, right? So the opposite is true for groups like, you know, carbonyls, mostly sulfoxide, cyanide, and I drew the nitro group here, right? The opposite's happening in all of these groups, right? Now you have a double bond that's conjugated with the double bond, right? And in this case, right, the oxygen carbon double bond, right? We know between this oxygen carbon double bond, this is a short bond too, right? So in this case, right, oxygen's electronegativity, right? You know how the resonance structure generally looks like this for carbonyls, right? And the whole reasoning for that is because in this case, oxygen is very electronegative. This bond is shorter. It's a double bond, right? It's going to want to have electrons, right? So essentially, the carbonyls are electron withdrawing groups because the oxygen, right, is withdrawing electron density from this carbon. You could consider this carbon partially positive or full on positive in a resonance structure, right? And then this bond, right, this pi bond or the pi electrons are leaving the alkene, right? So it's withdrawing electron density from them, right? So it's just a matter of whether you have lone pairs or like a group that can directly donate electron density, or if you have like double bonds that are conjugating electron density out of them, right? And if you look at table 18.1, for those who might have pulled out of it, right, you're going to see all these strong activators and stuff. They all have lone pairs directly next to the pi bonds in those phenyl rings, right? So those lone pairs can directly do like how we did this structure over here, right, is push in electron density, right, and make the ring more more electron rich. Same thing occurs for alkenes, right? So that's why these groups, right, they're known as electron donating groups, right? And then the opposite is true when you have carbonyl groups, because they withdraw electron density. Since the oxygen likes to be negative in that case, the carbon's very positive, right? Yeah, I mean, I never memorized any of that. I remember, you know, people would always try to memorize that chart for the electrophilic aromatic reactions, right? But like, I could draw this phenyl ring right now, right? Anyone know what this even is that I just drew? Anyone knows what TNT is? Dynamite. What Alfred Noble. Yeah, it's one of the components, I think, of modern dynamite, but it's a very powerful explosive. And it's what Alfred Noble made his fortune on. And then he realized kind of helped destroy the world. So he donated all his money to what is now known as the Noble Foundation. But anyways, this molecule, right, I could tell you that all these nitrogens in this case are electron withdrawing groups. So the only thing, I mean, in the case of nitro, right, the nitro structure, if I was to fully draw it out, right, it looks like, what is it? It's going to be N plus. So in that case, it looks like the nitro group is probably the only one you would have to kind of memorize, I guess, in a sense. Actually, I'll draw it in the single bond method. So you have O here plus here, O minus here, right? So as you see, that nitrogen has a positive charge on it. So electron density would want to come out, right? This would push it here, right? So I could tell you right off the bat without even looking at this that these are all electron withdrawing groups here, right? And then the last one is actually inactivating group. And that's where, you know, let's put an OH here, right? Then it wouldn't be TNT anymore. Then it would be like TN phenyl or something, trinitrophenyl. But I could tell you this is an activating group, right? Because there's a lone pair directly next to the ring, right? And if you, like I said, if you look at that gigantic table there, it literally has a, hold up, I gotta pull it up again. I don't know what happened to it. Yeah, like everything that's a strong activator or whatever in the top there, right? It's a lone pair directly next to the ring, right? And then what starts to make them weaker, right, is if they have any sort of additional conjugation. So if you had like a ester, so there's, just be very careful when you do this, right? It's all depending on the bonding, right? So you have a group that looks like this, right? Or you can have a group that looks like this. Right? So notice the location of what's the ester. In this case, it's one's on the phenyl's ring side and one's on the other side. Here, you have a lone pair directly next to it, right? But this is not a very strong electron donating group because yes, it can go in, right? But the electron density is also conjugated with the carbonyl. So that's what makes this what we consider a moderate one, right? So that's the difference between strong, moderate, and weak, right? Is if there's any sort of additional conjugation out of there. Right? And then here, if you notice, right, look at the location of the ester. This is a electron withdrawing group, right? Because now it has electron density being pulled out because the carbonyl is next to the thing. So it's conjugated out, right? So it all has to do, and this is not just for phenyl rings, it obviously applies to Diels-Alders, right? There's groups that, you know, can donate electron density into an alkene or like a pi bond, really, I should say. That's the general way to say it, I guess. So it can donate electron density into a pi bond or p orbital. And the bottom one, this one is a electron donating group, right? Because the lone pair is next to the pi bonds there, right? It's just not as strong because it's also conjugating out. So it can go both ways, right? In the case of like oxygen only, right, it can only go one way, which is, you know, towards this alkene or whatever, right? And then the last example is just what's it called? You know, simple R groups like ethyl or methyl or whatever, right? If you guys remember from carbocations, right, stability wise, right, what is the most stable? Tertiary, secondary, primary. What are generally stable? Tertiary, right? Reason being, because, well, I'll ask you guys, what's the reason for it? I said it earlier. Stability. I like that answer, actually. You're not wrong. Technically correct, the best kind of correct. It's hyperconjugation, right? If you want to look this up again in your textbook or whatever, but essentially it's when you have R groups, right? And I wish I could draw this sigma orbital here. So you have this MTP orbital here, right? And you have, you know, electrons from sigma orbitals, right? Essentially, they're donating electron density into MTP orbitals or p orbitals in general, right? And that phenomenon is known as hyperconjugation. And essentially, it's not as powerful as a lone pair donation, right? But it's a it helps in stabilizing positive charges, right? Because, electron density is helping stabilize something that lacks it, right? So that's why R groups are the weakest electron donators, because it's not a full-on resonance with like lone pairs or something like that. Or it's not a full-on like, it's not like full-on resonance or whatever. That's the only better way to describe the lone pairs. It's more of an effect that happens as a result of having sigma orbitals near pi orbitals, right? So these, you could think of these as giant clouds of electron density, R groups, like whatever type of alkyl groups you have here, right? And they're donating some of their cloud into, these alkenes, right? And same thing has to do with when you have more substituted. Well, actually, stability of alkenes is different. So I'll ignore that. But nucleophilicity of alkenes, right, increases when you are more substituted to a degree. Actually, ignore that part, because that has to do with breaking bonds and enthalpy and all that shit. Anyways, hopefully that clears up what electron withdrawing and donating groups are. We're going to get back to this in chapter 18, so probably next week if you guys cover it all this week. But yeah, it's just seeing whether electron density is going in or electron density is going out, right? So we're going to do aromaticity today. But I just want to do one example of the molecular orbital stuff that you will probably see on your exam, right? Yeah, ortho, para, meta, all that kind of jazz is next week. So one thing I like about Professor Biscoe and Andia, and I think even boson is starting to, go less on that. They don't do naming at this point. I mean, it's important to understand, right? So I will say you need to know the naming, in that if you're given a question where he writes out a name for you, right, you should, you have to be able to convert it if you can, but he'll never test you directly on naming. I think he stated that too. Right. So it's not like you're going to have the question on naming, but like naming is going to be a little bit important in this chapter, because it determines what substituents are at certain positions on a phenyl ring or benzene ring. Okay, so let's finish the last thing from chapter 16, which is, let me copy and paste this over. So this is from, that is what I'm doing, Madrona. Okay, this is from, what is this? So the 2018 exams are actually the ones I believe. There's no solution for this specific problem, but luckily for you, I will have the solution right now. Which is why I chose this, because the other one has a solution. What exam is this? ST. Exam 1, ST. Right. So it says, using molecular orbitals, show why the cycloaddition of 1,3-butadiene and ethylene, right, is thermally allowed, but the cycloaddition of 1,3,5-hexatriene, guess I was right about the name, is thermally disallowed, right? So this has to do with something you guys learned about the conservation of orbital symmetry, right? These are actually known as, I think, the Woodward-Hoffman rules. Woodward, what's his name? Robert Woodward is probably one of the most important and famous organic chemists of like 1900s, right? He's done so much work in synthesis and pericyclic reactions, and his kind of style of teaching, right? He would kind of be known for giving what's called Woodwardian lectures. I mean, they named it after him. He just, talk a lot about organic chemistry. Literally have well, the other stuff maybe, but like this is this stuff I'm pretty sure he covered, because I checked the syllabus. He told me to check the syllabus. This is 16.8, right? They're just called Woodward-Hoffman rules. I mean, it's part of it. The other stuff you guys probably, like I said, don't worry. It just comes under there. Don't worry. This though, I know he covered, right? Where he says, things are thermally allowed or thermally disallowed? Pretty sure, because he usually has this on his first exam. So just wanna, is that a yes or no, that he showed you something like this? Okay, making sure. So anyway, yeah, Woodward, like, it's kind of famous. Like he'd have like a bunch of chalk laid out on his desk and, just go talking about synthesis while smoking a cigarette during his lectures. That was a different time to be alive. But yeah, very interesting character, that Woodward. So anyways, he did a lot of his work on this stuff, and, him and Hoffman, they found that things need to essentially have symmetry between the orbitals, right? So you get what are called symmetry allowed and symmetry forbidden, right? And, a way you can kind of get around that is photochemically exciting stuff, right? So this question is kind of straightforward. It's asking you, right? Do the molecular orbitals in these things line up? That's when you're thermally why is this showing? Oh, right, I'm using white. Thermally allowed, right? Essentially is saying, okay, does the HOMO and the LUMO of these Diels-Alders reactions, are they in the same phase? Are they symmetrical, right? Do they line up properly, right? And if they do, that reaction is thermally allowed, which you see in the majority of Diels-Alder reactions, right? But then when you start using something like a triene or whatever, you'll see that's not the case, right? So he tells you that, this can happen, this can happen. You need to use MOs to show it. So let's start with A, right? And show why it is possible, right? So we have, what is it? 1,3-butadiene, right? So that has how many p orbitals, or, 4. So how many molecular orbitals do we expect? 4. Good. Right. So let's start drawing the MO diagram. Let's use a different color. Stick with the white. So 4 molecular orbitals, each with the p orbitals in there, right? Now, going from P1 to, you probably don't have to label them. This is just the proper notation, right? So the lowest energy level, right, has how many nodes? 0, right? And then going up, right? So I'm going to write here on the side nodes, right? And then going up, how many nodes do you get per energy level? 1, right? Which means the highest molecular orbital you have, the highest energy one, will have a max of MO minus 1 nodes, right? So the total number of molecular orbitals minus 1, right? So in this case, you have what? So I'll just write it here, MO minus 1. Right? So you have 4 molecular orbitals, right? Minus 1. You'll have a max of 3 nodes in the highest energy level, right? And we're going to see that in a bit, right? So the first thing, it's all about, this is all about waves, right? Because that's what orbitals are. They're wave functions, right? So things are either in phase or out of phase. So we're going to draw shaded stuff as in phase, right? So in the lowest energy level, everything is in phase with each other, right? If I were to draw this as a wave, right, this would look like this, right? It's one gigantic wave, right? And this is one part of the wave, right? Each of these are kind of endpoints of the wave, right? And everything in this part of the wave is in phase with each other, right? So now we need to create one node, right? Which means a node is essentially a position where you never find electron density, and it's a result of when you have orbitals that are in opposite phases of each other. So once again, thinking of them as a wave, right? This is a wave with 2 phases, right? This point right here is the node. Has anyone taken physics at this school or any point in their life and has seen this before, right? You have a positive phase and a negative phase. You guys see that? Or does anyone understand what I'm talking about here regarding to the waves? Yeah, okay, right. So this is what, it's not a positive or negative. It has to do with its kind of orientation in terms of its wave function, whether that wave function is positive or negative, right? Yes, a node is a place where there's no electron density, but that's not really too important. That's just for your understanding what a node is. It's the node is just something that forms when things are out of phase. So if you see here, right, we filled up 4 orbitals here, right? So this is the trick I was actually taught by Professor Zykes. Was now we have 4 orbitals, so 2 have to be in phase, 2 have to be out of phase, right? So 2 here, 2 here, right? So now these 2, oh, whoops, let's, oh, nope. Hell did I just do? Hold up. Here we go. I don't know why it took me to deleted notes. Anyways, there we go, reverse button. So we have 2 in phase, right? You could kind of consider the node in there. You don't have to draw it out because this is, I guess, a planar node. Is it a planar node? I have to check on that, right? 2 are out of phase. If you drew the wave through there, you'll see the wave looks like this, right? Now the next one, we need 2 nodes, right? So if the wave would look something like this, right? These are the 2 nodes, right? So we could have 1 orbital in here. You kind of just have to make sure this is all symmetrical. Then we could have 2 here, 2 here. Now you see how, like without even memorizing this chart, you can always get the phases, right? So this one right here, going to be shaded the same. This is going to be shaded the same. And then these 2 will be in phase with each other. So the nodes form here, here. You have 2 nodes there now. Last wave, right? You have 1, 2, 3 nodes, right? Put orbital here, 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 here. Everything is out of phase with each other. This is more important for the second. It's just a trick I wanted to show that if like, I don't like people memorizing stuff, but so this way you could always figure stuff out. So here in phase, out of phase, phase, out of phase. Oh wait, 1, 2, 3. Yeah. I guess you could draw it here. Yeah. Yeah.
Yeah.
What's up?
So this trick will this trick will always work for all the molecular orbitals when or any type of question like this one.
Yep.
Okay.
So now we just fill up electrons from lowest energy to highest energy. Boom, boom, boom. Right. And okay, let's draw ethylene on the side here. Okay, I mean, this one is simple. You can do it, but I'll show you the waves thing again, right? If we drew 1 wave, right, because we don't want any nodes, everything will be in the same phase, right? We want 1 node, we drew a wave, right? Nodes here, so that means both these orbitals are out of phase. So it doesn't matter what kind of molecule it is. How many electrons does this have? 2. So we fill this in, right? Feed 3 here will be the HOMO, right? Let's feed 2 here would be the LUMO, right? The HOMO, oh, sorry, I messed up there. It's feed 2 over here. HOMO is the highest occupied molecular orbital, right? LUMO is the lowest unoccupied. I mean, technically this would be the HOMO for this, and this would be the LUMO for this, right? Now let's zoom out a little, right? Which molecule is going to be the one that has the HOMO in this case? Diene, right? It's the electron-rich molecule. It's giving most of its electron density. Then obviously the other ethylene there will have its LUMO, right? So now what you can draw, right, is kind of it as an overlay, right? So we want to show the HOMO of ethylene on its structure, right? So now we could, now we just draw that orbital. So 2 are in phase with each other, 2 are out of phase with each other. right? Then we need to show, right? Remember, this is a kind of top bottom reaction, the way it occurs, right? So you could kind of show it coming below, right? And we want to show the LUMO, right? So if I draw it as is, right? Goes like this and this, right? But remember, this is happening in space. If you want, right, you could just turn this molecule around to make sure it lines up, right? What you can't do is break a bond or rotate the one orbital. You could rotate the full molecule, right? So just want to make that clear. Don't rotate this bond here to make sure the orbitals line up. You could rotate a molecule, right? So essentially I'm flipping it around, right? Where the orbitals, right, will just line up appropriately, right? Now you're just seeing it from the other side. Doesn't matter, but I mean, the orbital is still the same, right? One is in phase, one is out of phase, right? Just doing it from the other side, right? But I didn't rotate any specific orbital. I didn't break any bond. I just changed the face of the molecule, right? So now if you see, so the HOMO will always be the diene. Oh, sorry, right? So HOMO, right? This is the diene. It's going to be donating most of its electron density. And also, if you just look at it, it's more electron rich. It has two alkene groups. And then this is the LUMO, right? It's just a one single pi. I mean, it's just a double bond, right? It's 2 electrons here. There's 4 electrons here. The more electron rich substance will always have its HOMO. The more electron poor one will have its LUMO, right? So over here, just to be clear, we drew this, and over here we drew this, right? So now if you line up the orbitals with each other, you're going to see this symmetry allowed action. Because that is the highest occupied molecular orbital, right? That's what HOMO stands for. So literally the most filled orbital, right? We have 4 electrons here, right? This one there's no more electrons past this. There has to be the HOMO.
I just have a quick question. So for the diene that you drew, the specific p orbitals, like the phasing of it looks different than the LUMO of what's drawn above it.
What do you mean, the LUMO or the HOMO? This
LUMO.
one is the HOMO. I mean, we need the HOMO, right? So this is
Oh,
the
okay,
HOMO.
yeah.
Yeah.
That clears it up.
Nope, no problem. So this is the LUMO. So the HOMO-LUMO interaction, right? This is coming from top bottom. You see that the orbital phases line up here, right? This is like unshaded matching with unshaded, shaded matching with shaded. It's a symmetry allowed process. Therefore, it is thermally allowed.
A cool
Right?
question, if you don't mind.
Yeah.
How did you like line up the alkene, like the dienophile? Because this is the part that confuses me.
Mhm.
Like, how did you line up the p orbitals, the shaded, the unshaded?
So that's what I was saying earlier, but let me just draw out both. So technically, right, if you drew it like how we drew out the orbitals, it would look like this, right? Right,
Yes.
based on. So
We
what
got
I
it.
did was essentially I flipped the molecule. So the face, right, is if like you put your hand in, right? Like if you hold your hand out right now, the orbitals are lined up another way. If you turn your hand around, right, the shaded orbital is now on the other side. The unshaded is on the other side, right? Because remember, this is all happening in 3D space. They will line up to make sure they match up, right? We didn't break any bonds. We didn't rotate or like conform the molecule. That's just how they will line up.
So I can say that, like, for any example given or any question given, I can try and rotate the dienophile or the diene to make sure that, like, in any phase it can match up or not. And if it doesn't
Yeah.
match up in all phases, then it's
But
no
don't
match.
flip a single orbital, right? Don't do this, because if I flipped a single orbital like this here to this, then it would look like this, right? I rotated the molecule. You're allowed to rotate molecules in space, but don't break any bonds. Don't rotate specific orbitals. Rotate the whole thing completely, because that's just showing you different faces.
Got it. Okay, thank you.
Yeah. So just to be very clear on that, I rotated the molecule so the faces line up, right? And that's allowed, right? But you can't break any bonds or rotate any specific orbitals.
Is heat the same as H nu? I mean, H nu is light, right?
Yeah. So
That's-
heat you will generally see represented as delta. I mean, I think some people do represent it as thing, but generally you'll see light as like H nu or whatever.
Like he is not
Uh,
really doing anything to this, right? Is it, or is it just like something that you just have to put there, but it doesn't really like? Because
I
I know,
mean,
like,
you just need a elevated temperature for these reactions. You'll see most Diels-Alders are happened at like, you know,
because like I know
100
like
degrees
light,
plus.
like light actually like changes the HOMO and LUMO around. That's why.
Yeah,
So
so when you have like UV light or whatever, I don't know. I don't know if that is, it's usually represented like that, where you could just write UV or light, right? It's literally, you know, light is energy, it's photons. It's gonna, you know, give energy to whichever molecule needs to be excited, right? And then it's gonna push an electron up from one orbital to the next, and then you are now changing what is the HOMO for the certain molecule, and then, you know, you're gonna see that under photochemical conditions, things will be chemically allowed. So those reactions, you literally, the way you do them is you put them in a temperature bath or whatever, and you literally put like a light bulb, like a UV lamp next to them, right? And that light is giving it extra energy. And now there's more kind of advanced chemistry that's called photoredox chemistry. It's essentially, you can do a lot of sort of organometallic reactions with the help of certain wavelengths of light. But anyways, that's far beyond what you need to know for this course. I'm just kind of mentioning it. But yeah, the main thing is diene HOMO, dienophile LUMO. Okay. Let's do the other part, why it's disallowed. Okay. So this interaction, you can, I mean, if you want to just make sure, just check, right? Just make sure the phases line up. Once again, I cannot say this enough. Do not break any bonds here. Do not flip one orbital and just one. Rotate the whole molecule and make sure you draw it right. We'll do it again in the next one too, right? So the next one is going to have a lot more orbitals in them. That's okay. So this is, what was it? Okay, I want to make sure I finish this up before 1. We'll take a break and then we'll be able to knock out all of chapter 17, because that's mostly just understanding what aromaticity is. It's chapter 18 that I want to make sure I spend all of next week on. Okay, so what is this? Plus this, right? So now we need to draw molecular orbital diagram for 135 hexatriene, right? How many pi electrons does it have? 6, which means how many, or not pi electrons, 6p orbitals. So it has 6 molecular orbitals. No, let's switch back to white. Copy. Screw drawing all of those out again. Here we got there 4. 5 and 6. Got 6, right? Okay, cool. Damn it. Friggin' eyes tearing up again. Okay, so we have 6 molecular orbitals, we got to fill them out. So this is where the wave method comes into much better play. Because if you want to memorize that, you know, go for it. Like, bam, you know, got some amazing memory there. But I'm inherently a lazy person, so I hate memorizing stuff. 1 wave, 1 node there, 2 nodes. Now this should be, we have 2 nodes here. So this is 0, 1, 2, 3, 4, and 5, right? So 2, 2. Let me just draw out the wave here before I draw it. 3. Okay, so we want 2, 2, 1, right? So it would be, oh, messed up there. 2, 2, there we go. 3 nodes, right? So a node here, 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 right? Now we need 4 nodes, right? So it would be, right? So 1, 2, 3, 4, right? We have 6 orbitals, right? So we want 1 here, 1 here. Oh no, we could have 2 here, 2 here. So we have F5. Probably be 2 in the middle. Let's see. 1, 1. There we go. Thank you. There we go. So you just have to conserve the symmetry, right? Oh, I don't know why my thing's messing up. Take off my charger. But that's why I try to drive the wave in the side, right? It's a little bit easier because then you could fill out the orbitals, right? I was just trying to overlay it, but so it's 2, 2. I'm sorry, it's 2 in the middle, and then the other 4 are individual, right? So that, so 4 nodes, and then the 5 ones. The last and first are always the easiest, right? Because there's just a node in between every orbital, right? Now we just fill out the phases, right? See how much easier that is than memorizing all this. You could go check any diagram out, right? And I will tell you that is the exact molecular orbital layout for 135 hexatriene, right? If I'm wrong, I'll give you $5. Yeah, this works for a lot of $5 each. Yeah, 5 is too low. This works for almost all molecules with like p molecular orbitals. 5 points on your exam. Now that's a better thing. Unfortunately, I do not have the ability to negotiate that. So I think Madrona asked earlier, how do you know which one is the HOMO? Same thing here, right? This has 6 electrons, right? So this is the HOMO now. This is the LUMO, right? You don't have to really worry about the other ones. Oh, sorry, 6, right? So HOMO is just the one with the last set of electrons, and in this case, it's the 3rd orbital, right? So we did the one before. I'm just gonna draw it out here again.
Sharuk, I have a question.
Yeah, what's up?
How do you know how far is to go when it comes to the electron pairing? Like I understand I still don't understand why we stopped at 3 for this one.
So electrons come from where in these molecules? The pi bonds, right?
Mm-hmm.
How many are in each?
Oh, then okay, sorry. That was a dumb question.
No, there's no such thing as a dumb question. It's fine. There we go. And there's only 2 here. So this is our LUMO, this is our HOMO, right? Now we have to draw out the HOMO for this. So that's Phe3, right? Let's draw it out on top of the molecule. Okay, 1 second. This one's a little bit harder to draw out. There we go. So we have a double bond here, 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 right? Now we can draw out the orbitals.
Can you go up a little?
Yeah, I'll zoom out.
Oh, thank you. Better.
Yep.
Thank you.
So we're starting from, so these 2 are in phase with each other. The middle two are out of phase, the end two are in phase as well, right? Now ethylene, we need the LUMO, right? One. Oh, sorry, wrong way. Right? So now, right here, I'm gonna draw this. Paste this so I show you what I mean by the rotation in this case as well, in case it might be confusing to some people. Right? Is no matter how much I rotate this molecule, right? If I change this, right, to the other way around, right? Just like this, right? Essentially I rotated the ethylene. These phases, they will never match up. Let me actually move this a little bit more downwards. Right? No matter what's face of this molecule, right? These orbitals will never match up because these are both like unshaded, right? And the ethylene, no matter which way, whether you flip it up, down, or anyways, right? There will always be one in phase and one out of phase, right? So this is not allowed. So you could say it does not have orbital symmetry or not thermally allowed. Must use, you could, this is enough to answer the question. You could say must use photochemical, or you don't have to write the second part, but to do reaction. Not thermally allowed, right? So it's all about matching those orbitals, right? So either way, I flipped it around. Even if you flip this around up and down, you're gonna see both sides are in phase or out of phase, right? So hopefully that gives you guys everything from chapter 16 in terms of Diels-Alders, inside outside groups, the endo stuff, conjugated alkene systems. What did we do? Kinetic and thermodynamic product. For node pour, so level 4, is it possible to do up, down, down? That does not symmetrical, exactly. Right? You have to keep them symmetrical. That's the one main thing in all these orbitals, right? If you left from right, there'd be symmetrical. Yeah, what's up?
For the LUMO of the dienophile, the first node is shaded on the upper side.
Well, none of the nodes are shaded. Those are orbitals.
I'm sorry, the orbital.
Yeah.
It's shaded on the upper side, and the other one is on the lower side.
What do you mean? Like,
Can you go up a little? Yes. Do you see the LUMO in the one you drew?
yeah.
So why did you change the orientation there?
What do you mean I changed the orientation? It's the same as the one.
You flip the whole thing together, all together. Here.
I'm not sure what you mean.
She means like rotating, like
Oh, then the bottom one.
yeah.
Yeah.
They
Yeah,
rotated the entire molecule.
Yeah, that's what I was saying. It's even if you rotate the molecule, it's never going to be thermally allowed, right? So because someone was asking before, can you always rotate it to make it match up, right? So in this case, no matter whether I rotated it from one side or the other side, it's never going to match up. Right?
Yeah, but you said you have to have the shaded towards the shaded and the unshaded towards the unshaded, right?
Yes.
Okay, so the upper one you drew, the unshaded is towards the shaded.
Oh, you mean, oh yeah, technically, yeah, you could say these line up, but the other one doesn't. Yeah, okay, yeah,
Okay.
That's what you meant. Yeah, technically, yeah, these and this wouldn't line up. I guess you could say this is check, but I just consider the whole thing not allowed, right?
Okay,
But yeah.
So if only one lines up, that still doesn't count.
Yeah,
right?
so if only one lines up, it doesn't count. You need symmetry at both ends of the molecule. Yeah. Thank you for pointing that out. Okay, so yeah, that should be it for 16. Take like a 5-minute break and then we'll go into aromaticity. So that question example If you do see it on your exam, that should more or less, so this is the highest level of molecular orbital you'll probably get. I've never seen anybody do 8, right? Who knows? But I don't think Professor Bisco would do that, because he knows there's a time limit. And, he's very attentive to students' needs. So that's the highest you'll ever go, right? And this should cover more or less all cases of this problem, right? So there's another problem, some of the other practice exam, definitely try those out. But, this part right here should show you how to always do this problem correctly, right? So just make sure those orbitals line up. They're symmetrical on both ends, right? Both have to pair up, right? You could try flipping around the molecule as long as you don't break any bonds or rotate one orbital. You could rotate it, flip it completely, right? If it lines up, it lines up, right? But if it doesn't, it doesn't, right?
So Farouk,
Mhm.
would you say the rules are that if they ask a question like this, as you just showed, the rules
Yeah.
are as follows: that when doing the molecular orbital, it has to be symmetrical throughout the entire thing.
Yeah.
Um,
So the ends
then-
of each molecular orbital, right? Because that's where this reaction is happening, right?
Mhm.
They have to have orbital symmetry, right?
Yeah. And then we
Uh,
look at the homo and LUMO states for both the diene and the dienophile.
mhm.
And okay, and they have to, and like has to match with like in order for it to be thermally allowed.
Yeah. So if they match as is, right? So this is all, nothing is excited here. Everything is in its ground state, right? So everything when it's in its ground state is thermally allowed, which makes the reaction good because all you need to do is heat it up and boom, you'll get a product, right? But if it's not thermally allowed, right, the way you could kind of get past this, right? So, I'll just show this right now before we take our break was, if I need to copy this entire thing on the side so I don't mess this notes up here. So if I took this, copy that, let's do it let's do it below. It's fine. Right. So if we wanted to what the heck? For some reason my eraser wasn't working, right? We wanted to show what would happen if you photochemically excited this, right? What would happen here, right, is you have some sort of form of UV radiation or some sort of form of photochemical radiation, right? One of these electrons, I'm going to draw this arrow, right, it's going to jump up here, right? So now this, right, let's draw this as the other one too now, right? It's now in its excited state, right? And now this, technically this is called the semi-unoccupied molecular orbital or semi-occupied molecular orbital. But in the case for excited molecules, you now consider this the HOMO, right? Because now this is the highest occupied molecular orbital, right? Phi4. Now, if you look at Phi4, right? And if we draw all the orbitals on it, right, you'll see why this is now photochemically allowed, right? We draw this, what is it here? This is this, and this would be this. And this, right? Wait, did I draw the right one? No, I did not draw the right one. Whoops. Second. Drew the one above it. Okay, so that, then these two, right? And this, right? So now if you line it up with ethylene, so that's why it's photochemically allowed, because once you excite the molecule, right, it's going to go ahead and orbitals will line up. And this is why it all works from thermally and photochemically allowed, because usually the next orbital up will line up with the LUMO of the electron pore species. So that gives you a little extra in case you did get asked that on your exam about photochemical stuff, right? That's how you would do it. You bump it up, then the next highest orbital above the traditional ground state HOMO is now the new excited state HOMO, right? And then you use that to line it up and you see that it's photochemically allowed. So if you get asked the question, is this thermally allowed or photochemically allowed, right? If it doesn't work thermally, then you excite the electron to the next orbital level, right? Then you check it with that. If it works, then your answer will be it is photochemically allowed, and you show that entire stuff. Okay, let's take a break till 1:10, and then we will start chapter 17. While we are on this break, realize in one of my old chapters or whatever for this notebook, I did have a thing for EWGs and EWGs. So electron donating groups, electron withdrawing groups, right? So something a lot when you will be showing up a lot when you're going forward. So, what is it? So yeah, majority of reactions are things that are between things that lack electron density and things that have it, right? So, you know, this table, like I said before, right, has kind of everything on it. Oops. Right, so essentially the top portion there are electron donating groups. The bottom portion are electron withdrawing groups. The halogens are a little funky though for just for aromatic reactions, right? So if you scroll down this, like I said, you don't have to memorize all this. Just learn the logic behind all the structures here. So I have all this stuff kind of written out. If you guys want to go over that in one of the review sheets here. I honestly forgot I even wrote this. This was like so long ago. Yeah, spring of 2020. Yeah. Anyways, it's there for your use. So this, I'm actually gonna copy again. Second. Okay, so we're gonna start off with this page here. Go back to the session. But chapter 17, so identifying aromatic compounds, right? Most drugs in the world have aromatic rings, right? Most biological molecules, it's one of those things, aromaticity exists everywhere, right? So, I mean, essentially things are divided in organic chemistry. Yeah, perfumes. Well, perfumes are mostly like esters or whatever. Some of them do have aromatic rings, but usually a lot of their stuff are from ester groups. But I mean, I don't know too much about cosmetic chemistry, so, but I'm sure there's probably perfumes that use aromatic. So it's not aromatic in the sense, right? And I understand why you probably said perfumes, right? It's not just the word we use to describe them, because as before, those were, you know, things that had some sort of smell, right? But you know, anyways, so I just want to go over this before we do some practice problems, right? So the criteria for aromaticity, right? It has a planar ring that has overlapping p orbitals, right? So if you see benzene here, right, everything is in a flat plane, right? And if we drew, this is benzene on the bottom here, right? If we drew these orbitals on top of benzene, you'll see that everything is in a circular flat position, right? And they're all overlapping with each other. Essentially, you'll see electrons, right, are buzzing all the way around through this ring. You're going to actually see benzene has interesting properties because it like creates one portion of the molecule that has electron density stirring through it, and then the other doesn't. And then, you know, it has all sorts of, I think it's called diamagnetism or some stuff like that. But anyways, example 2 here, cyclopentadienyl carbanion, right? It's the same thing. It has a system of overlapping p orbitals, right? Position A there, right? That's a negative charge, which is just a lone pair, right? And it has a lone pair and a p orbital here, right? And this is the key point I want to go over before we do practice. P orbitals are not exclusive to pi bonds, right? Look for carbocations or carboanions, right? So you can find a p orbital at a positive charge or a negative charge, right? Could be, it's not just at the end of each pi bond. And then the last thing, essentially the 2 criteria is, first, if it doesn't meet criteria 1, it's non-aromatic or it's some sort of aliphatic carbon, right? Then once you meet criteria 1, then you check Huckel's rule, right? Which is essentially Huckel numbers, right, are things that obey 4n plus 2. So common ones here I listed, 2, 6, 10, 14. So these are for n equals 0, 1, 2, and 3, right? So if it follows 4n plus 2, you can label that molecule as aromatic, right? And then anti-aromaticity, right? is kind of the opposite. It obeys for n, right? And if that is for something like 0, 4, 8, or 12 electrons, right, where n equals 0, 1, or 2, or 3. And those we call as anti-aromatic, which are more stable or less stable than aromatic compounds. Less stable. Okay. And then you have non-aromatic. So this is what I wrote out is if it doesn't obey rule 1, it's automatically non-aromatic, right? So something like 135 135 hexatriene, right? No ring, no continuous overlap. Same thing here. If you see like, the cyclopentadiene, right? Or cycloheptatriene, I believe that one's called, right? At position X there, it's an sp3 orbital, right? So it's a ring, it has multiple bonds, right? But at that position, it's not flat anymore, right? It's an sp3 hybridized, right? Everything has to be sp2 hybridized for it to be flat all throughout, right? So it has rings and p orbitals, but doesn't have a continuous overlap, right? So examples like that. And then the only exceptions you guys kind of need to know is like 8 annulene and 10 annulene, right? So you see this is a diagram taken from the book, right? It follows a boat structure, right? Because it's big enough to conform, right? So you might think it's anti-aromatic, right? But it actually is non-aromatic because it's not planar, right? And then 10 annulene is the only exception to kind of aromatic stuff here is even though it has 10 pi electrons, so it fits 4 and sorry, what's up? Eight annulene. So you would assume it's anti-aromatic because it has 8 electrons. It fits criteria 1, right? But this is just the nature of this molecule. And chemists actually observed it, is they found out it doesn't actually. It's not anti-aromatic because it actually conforms to this boat structure here, right? So instead of being flat, despite it being, looking like it fills criteria 1, it actually conforms into this kind of boat structure, right? And none of these p orbitals, right, are in a flat planar ring. They're now in a conformed ring, right? And that automatically disobeys rule 1, right? So that's one exception. And the other one is 10 annulene, which if you look at the structure, right, is a kind of a big ass 10-membered ring, right? Has 5 pi bonds, 10 electrons. So you think it's going to be aromatic, but as I highlighted there, the 2 hydrogens there, right? They have steric interactions, right? I don't think you could call them. I guess you could call them Gaussian interactions, right? And that increases the energy of the molecule a lot because it's already very strained. So what happens is the molecule also, it conforms out of a planar, like it's not planar anymore. It conforms out to prevent those steric interactions, right? So these are the only kind of 2 exceptions you need to know, right? Is 8 annulene and 10 annulene, right? Because of conformations, yeah, exactly. They become not planar and disobey rule 1. Therefore, they're non-aromatic, despite looking anti or aromatic. Okay. I guess we could actually do this practice problem I did here. Okay, identify whether the following molecules are aromatic, anti-aromatic, or non-aromatic. So actually, this one is kind of debated. So I'm gonna actually remove that one there because I have to actually ask Professor Bisco about that. But here, first one is benzene, right? So let's do this one together. Simple enough, right? Oh, he did that one? Oh, okay. And did he say it was anti? Okay. All right, then we could. I mean, if he did that already in class, it's fine. Right? Yeah, because some people were. I remember someone was trying to argue that it's technically non-aromatic because it's, it could conform to sp3, but I was just like, it's a carbon ion. That lone pair has to be in a p orbital, and therefore it's anti-aromatic. But we'll get into questions like that, when to know when things hybridized. This is a very basic question since they're all carbon cycles. So the first one, benzene, it has 2, 4, 6, right? So it has 6 pi electrons, right? Does it obey rule 1? Yes. So if it obeys, oh shoot, we should have. Okay, don't do what I just did. First thing, let's always do rule 1. Does this obey rule 1? Yes, right? Because it has a p orbital at every position here, and we know it's a flat molecule, right? So rule 1, check. Rule 2, it has 6 pi electrons. That fits for 4n plus 2 for n equals 1, right? So rule 1 is check. If it's a Huckel number, therefore it is aromatic. Now this one, does it fit criteria 1? Yes, right? We have,
Sharuk, sorry, you put
Yeah.
4n plus 2. Is that supposed to be 4n minus 2 actually, or am I
no,
lazy?
it's 4n plus 2. That's
Oh,
the
okay.
formula for Huckel's number. The other one is 4n. Okay, that was a horribly dropped orbital there. But anyways, right? We have p orbitals at the end of each pi bond, and remember what I said? When you have a positive, what's it called? Carbocation there, right? It is what's not shown as technically the hydrogen bonded, and that p orbital is empty, right? So carbanions, p orbital is just filled with the lone pair. Carbocations, the p orbital is filled with a nothing. Sorry, it's not filled, right? But there is a p orbital there, and we know the geometry of carbocations is what? Okay, what's the hybridization? It's sp2, and it's trigonal planar, right? So that kind of proves it's planar. So yes, it fits criteria 1 here, right? So criteria 1 is check. How many pi electrons does it have? 6, right? So is this aromatic or anti-aromatic? Good. Just to quickly do this one, rule 1 is check. 2 is 4, it's anti. It's for future notes. Okay, this fourth one here, does it fit criteria 1? Nope. Why not? sp3 carbons here and here, right? So what is this? Unaromatic. Okay, does this fit criteria 1, the last one? No, right? This is one of those exceptions we learned, 8 annulene, right? Like I said, those are 2 the only exceptions you need to know, right? Even though it looks like it, it does not fit criteria 1 and is observed as a non-aromatic molecule. Okay, so I guess we could just continue down so you have all the aromaticity notes in this. Let's pull out some problems now from the textbook in terms of hybridization theory. Related to hybridization theory, I guess. Okay, so 17/13 is one I like doing. So let's start with A, right? Because this is where, once we get the heterocycles, that's where people start getting confused, right? Because they're like, what do I do with the lone pairs, right? But it's not that bad, right? You just have to think about it, right? So here we have this molecule, right? This is furan. Pretty sure it's furan. So how many electron? Okay, first of all, I'm trying to describe how I should say this first part because I don't want to say just to go and check if it's aromatic. Okay, so anyways, if you want to look this up, this is called furan. right? So first, let's just look at pi bonds. It has two pi bonds here, 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 and here, right? So from pi electrons, but yeah, you're right there, Madrona. That's essentially what I'm trying to get at. We have how many electrons from pi bonds? 4, right? So now the remaining thing is there's an oxygen there, right? So if we were to include one of the lone pairs from oxygen, would this make the molecule more stable or less stable? More stable. And why is that? Because it's going to be aromatic. So this is one thing I want to clarify is when you have a heteroatom with 2 lone pairs, right? What determines if it's going to be sp2 or sp3 is if it makes the molecule aromatic. If it makes the molecule aromatic, it will be sp2 hybridized. Let me just be clear again. Only one lone pair will be in a p orbital, right? So if I drew a p orbital here, right? One lone pair is in a p orbital, right? And what orbital is the other lone pair in? Think about it. What's the hybridization of the molecule? So what kind of orbital does the lone pair have to be in? sp2, right? It's an sp2 hybridized orbital, or a molecule, right? Atom, right? If this atom is sp2 hybridized, right? It has the p orbital coming out. And then the other lone pair has to be in an sp2 hybridized orbital, right? And that's going to be outside of the plane of the ring, right? You saw this in pyridine, right? But if you were asked, this question, right, specifically, one lone pair is in a p orbital, right? So this is a sp2 orbital. This is a p orbital, right? The p orbital will participate in aromaticity, that lone pair, right? The sp2 orbital is outside of the plane of the ring, right? But just to be clear, only one lone, if you have 2 lone pairs, only one can be in a p orbital because that's just how orbitals work, right? Orbitals can only have up to 1 pair of electrons in it, right? And this can only have 1 p orbital, right? Therefore, there can only be 1 lone pair in it, right? So never put both pairs of electrons in your p orbitals, right? It's not possible, right? So if you were to classify this molecule, what would it be? Well, we kind of just wrote it out there, aromatic. So same thing. So the question asked here, sorry, this is sulfur, right? Let's draw these, purple and orange, right? What kind of orbitals are the electrons in? I guess it really doesn't matter which one you pick, just be consistent. So yeah, it's the same thing. It's just the sulfur analog of furan, right? This is called, I think it's called thiopene. Somebody could look it up, but I'm pretty sure it's called thiopene. But same story here, right? Is that one lone pair can occupy a p orbital. So let's draw that out, right? Let's use blue maybe, right? And then the other is going to be in an sp2 orbital, right? So that will make this entire molecule aromatic, right? Because of its 6 pi electron, and we know this is now sp2 hybridized. The other lone pair is going to be, what's it called? An sp2 orbital. Okay. Okay, let's do C. Damn. This one's a little hard to draw. Okay, so there's a lone pair on nitrogen. It'll take a little time. Send me the answer directly. So that way you don't give it to other people who might be working on it. Is the lone pair going to be, what kind of orbital will the lone pair be in? And will it or will it not participate in aromaticity? Okay, any more people? Okay, so it seems like everyone who sent a message there is on the right track, right? So let's count the electrons from the pi bond. So you have 2, 2, 2, right? So at all those carbons at this point here, we're planar to that degree. So this would be 6 pi electrons already in this molecule. So now we have the lone pair from nitrogen. If we put it in a p orbital, right, it would make this molecule what? You guys can switch back to all chat now. Anti, right? Because now we have additional electron that's +2. That would make it 8 pi electrons, right? And that would make this anti-aromatic. So this is where, that's why he goes into hybridization theory in the beginning of the semester, because it comes back into play so much. Things constantly rehybridize themselves, whether it's to fix their angles or it's make them, essentially it's always to make them more stable. Like nature prefers the lowest state of potential energy, right? So things will always change themselves in a way to make themselves more stable or, you know, less strained, whatever that might be. So in this case, right, if this wasn't a p orbital and nitrogen was sp2, that would make this entire compound anti-aromatic, which is something we don't want. So instead, nitrogen will be sp3 hybridized, right? And this lone pair, right, would be in a sp3 orbital, right? Does not participate in aromaticity. It's non-aromatic. Because now, remember what the first rule is, right? It has to be planar. If this nitrogen is sp3 hybridized, you broke planarity in the ring. Right? So if something can avoid being anti, it will. Exactly, right? Always. But sometimes you're locked into anti-aromaticity and you can't do anything about it. So usually for heteroatoms, right? So when you have like nitrogen, sulfur or oxygen present in your molecule, right? If like there's a chance to make it, like if you expect it to be anti-aromatic, it will actually conform out, become sp3 and the molecule will stay non-aromatic, right? So yeah, in general trends of stability. So most stable is aromatic. That's the general trend, right? So most stable is anti-aromatics, then non-aromatics is, aromatics, non-anti, right? So this is just a general trend. It all varies from molecule to molecule, right? Maybe you have a super strain, like, you know, electron dense non-aromatic, but generally you could say aromatics are more stable than non-aromatics, which are more stable than anti, right? And things, if they can prevent themselves from being anti-aromatic, they will rehybridize to break planarity so that it doesn't fit criteria 1 and they will become non-aromatic. Examples of a locked in anti-aromatic compound is cyclobutadiene, right? We have p orbitals here, right? None of these carbons can rehybridize themselves. They're all locked into sp2. We have 4 pi electrons, right? It fits criteria 1, right? And it can't conform out of criteria 1 because everything is stuck in sp2, right? If it fits criteria 1, right? And criteria 2, it matches for anti. So that's how you end up with the anti-aromatic, right? And on your test, if you do get like a heterocycle, like example C here, right? You know, if you just make sure to show that or point out that the orbital, I mean, that nitrogen or whatever, right? Or whatever oxygen, sulfur, whatever you might have, just make sure to point out that it's going to be sp3 hybridized and that's non-aromatic, right? So that's very clear. So that will give you points because in case I don't think he'll ever do that though. Like he'll make sure to give you definitive answers. Because generally, Professor Biscoe doesn't like he doesn't make up, and even boson, they don't like make up examples. Everything they do is usually in literature, right? So like they know that that's the product you're getting. They know this is correct, right? So anyways, let's do one more. Let's see. Oh, actually, this is a good example right here is G. No, not G. Let's do G, F and G. So F, right? Whoops. Right. So the lone pairs here are here. So take a minute or two, send me a direct message and tell me if they participate in aromaticity or not. And if they do or do not, tell me what orbitals you expect them to be in. Okay. So I'm glad we have mixed messages here to clarify what's happening in this question, right? So first thing, right, is let's look at the molecule. It has there's a 1, 2, 3 pi bonds, right? So there's 6 pi electrons, right? Right. Both these nitrogens are automatically locked into sp2 hybridized states, right? Because look at them, they have pi bonds, right? This instead of nitrogen, instead of a carbon, this is just a nitrogen, right? So this pi bond, right? That's a p orbital. That's a p orbital, right? So nitrogen's p orbitals are being used in pi bonds. Its hybridization is locked into sp2. So think of this as benzene, right? Except 2 carbons are just nitrogens and they have a lone pair because that's just the valence of nitrogen, right? So nitrogen's p orbitals are already in use here, right? So yes, the total compound is aromatic, right? It has 6 pi electrons, but these electrons, right? They can't participate in aromaticity, right? Because they're in sp2 hybridized orbitals outside of it, right? The p orbitals, to make this very clear, the p orbitals of nitrogen are being used in pi bonds, right? So those lone pairs cannot be in p orbitals, right? Then it fits the rest of the criteria. It's planar, it has an overlapping system of p orbitals, and it has a Huckel number of electrons. So the whole molecule is aromatic, right? But the lone pairs do not participate in aromaticity, right? They are outside the ring of the aromatic electrons, right? So some had mixed answers here, right? Some said they're like aromatic. Some people had the right completely right. Some people were saying, they're aromatic, and like, it's a total of 12 electrons, right? But just to be clear, this molecule is aromatic because it fits both criteria. Nitrogen's p orbitals are being used. I'll write this here. P orbitals are in use, right? So they have to be in sp2 hybridized orbitals outside of the ring, right? And they do not participate in aromaticity, right? So what do you mean? So if one of them is sp3, then it would have to have a single bond. So it would look something like this. Oops. Then you have this, right? But at this point now, right, this carbon here, right, is sp3 too, right? If that was an example you're trying to go for, right? Because as soon as you remove that double bond, the other carbon next to it is not going to be sp2 as well either, right? So that entire molecule is just non-aromatic. But to be clear again, they are outside of the ring because the p orbitals of nitrogen are already participating in the rest of the structure, right? That's what pi bonds are, right? You have a sigma bond, which is an overlap of your main orbitals, right? And then the pi bond, right, is your overlap of your p orbitals, right? It's not as good as okay, sorry, this is the sigma bond actually, right? Ignore that stuff in the middle, right? So that's your sigma, right? This is your pi bond, right? It's a small partial overlap of p orbitals, right? So the molecule total is aromatic. It's not anti-aromatic. Those electrons are not pi electrons, Madrona. They're the only pi electrons here are from the double bonds, here, here, and here, right? The other one is non-aromatic. This is an sp3 hybridized carbon automatically. So you can just ignore everything because at this point you have an sp3 hybridized molecule, right? Let's do one more example, right? That's why I like doing this hybridization example because it kind of gives you like every little bit at this point that you could deal with aromaticity. Okay, so this same thing. Tell me first the state of the molecule. Private message me, right? Whether it's, what if it's aromatic, not, or anti, right? What is do the lone pairs participate if it is or not, or what kind of orbitals are they in, right? Just tell me if it's aromatic or not, and if it does, explain the rest. And you can send me that. So think about this clearly though, carefully though. And then we're gonna do problems again like the first set. I'll do them directly from the exams, how you would be asked this on exams. So let me actually, while you guys work on that, go and find exams for us to grab stuff from. Oh, I love the dipole questions. Yeah, we'll do one example of those too, because I know he likes doing that. Oh, and we'll do acidity questions as well. Okay, yeah, we have a couple of different questions to do here. That's why I love this question. This is actually one of my favorite questions in the textbook. Because it always gets mixed answers, and it's a good way to always clarify this topic. So let's go over it. I think you guys can switch to all chat now. God, man, my eye is killing me. I have this thing called like corneal erosion syndrome or whatever. Essentially, my eyes get super dry. So I guess when I go to sleep or whatever, like my eyelid kind of like brazes over my cornea, and it like just makes it like super just messed up or whatever. So I gotta put like a bunch of ointments and drop. And right now it's just literally tearing up as I started this lesson. Just annoying. Yep. Okay. Give me a second. Sorry. No, I wear glasses. I was actually trying to get LASIK, but now because of this, I'm not a candidate for LASIK anymore. There's actually another procedure that my ophthalmologist told me that you could do if you want to like not have glasses anymore. I forgot what it's called, but yeah, I can't do LASIK because then I'd probably go blind. A blind chemist. Anyways, yeah, so let's go over this, right? So first we have 2 pi bonds here, right? So we could say we have 4 pi electrons from those, right? Now let's look at the oxygen here. And people had mixed answers where they said, okay, one is going to be that, one isn't, right? Now the thing with the oxygens here, either you can make them both sp2. Well, okay, let's start with one. Let's say we made this top one sp2 hybridized, right? And a few people sent me this answer, right? They're like, okay, one is sp2 hybridized here, right? As a p orbital, this would be in an sp2 orbital, and then the entire molecule is aromatic. But is it, right? Because here, right, if it's going to be, in order for it to be aromatic, right, the other oxygen, right, has to be sp2, right? So let's make the other oxygen sp2 as well too. We'll put one in a thing, one in a p orbital. Oops. Right? That's criteria 1, right? And if it's going to, now it fits criteria 1, both oxygens are sp2 hybridized, right? So in order for it to fit criteria 1, you can't pick and choose which oxygen is that, right? If you leave one as sp3, it automatically disobeys criteria 1, right? But if you wanted to fit criteria 1 and you make them sp2, they both have to be sp2. So as people in the chat have now said, then it would be anti, because now we have 4 electrons from the pi bonds, 4 from lone pairs, right? Total of 8 total pi electrons, right? Which would make it anti. And things don't want to be anti, right? So instead, what happens is both oxygens, and a few people got this right? Both oxygens are actually sp3 hybridized, because this molecule is going to stay non-aromatic. It doesn't, because if you made them both sp2 to fit criteria 1, it would be anti, right? It would not, you can't pick and choose the oxygen. You can't pick and choose any atom, I should say. It's not just oxygen, right? Either they're all planar or they're not, right? So a lot of people always make this mistake. So it's not like, don't sweat yourself if you got it wrong. It's always happened in the past, right? So to fit criteria 1, everything has to be planar, which means the other oxygen has to donate one of its electron pairs as well, which would make this entire thing anti. So instead of doing all of that, right? Let's erase all these orbitals, right? Everything here is just sp3 hybridized. So this is sp3, this is sp3. Now we got a nice non-aromatic compound, right? And all these electrons are in sp3 orbitals, right? So just be careful of that. You can't pick and choose, right? Because if you made one sp3 and the other sp2, as Ali there said, right, then it wouldn't fit criteria 1 and it would still be non-aromatic, right? So
Wait, it's rude because this is non-aromatic. Just want to
yep,
clarify.
it's non-aromatic.
And it's because of the oxygens being both sp3.
Yeah, right. Because if they were both sp2, right, we would have an anti-aromatic compound. Because then you can't like say, okay, I only want one lone pair from one of the oxygens, hold the other one, right? You have to have both of them, right, to fit criteria 1. So the entire molecule will choose to be non-aromatic because otherwise, if you'd made it planar, if you made everything sp2, right, it would have total of 8 pi electrons, which is no bueno. So yeah, there's more practice for this and the second language and the textbook for the hybridization stuff. What does it say under 4 pi? So maybe I should 4 pi bond and 4 lone pair. It's a total of 8 pi electrons, right? So there's 4 electrons from pi bonds, 4 electrons from lone pairs. That would make it 8. And we can't have that, right? We don't want it. And we have an option to rehybridize to sp3, so it will. And this makes it non-aromatic. Okay, let's do exam questions that you guys will see on your exams. And for those from bosons here, I don't know if there are any people from bosons. He kind of has similar rank the aromaticity questions as well too, right? I mean, all the stuff, I'm going over is going to be covered in both classes, right? Just the structure layout might be like different, but I don't have many exams from boson, so that's why I'm just using these exams. So let's start with question 1. This is 2018 exam RS. Hey, did I put it in the right thing there? Oh wait, we're in the. I just forgot we switched to. Okay, so label the following species as aromatic, anti, or not. So let me make sure I have open chat here. Everyone could just send this directly in the class. So let's start with A over here, right? Which one is it going to be and why? Oh, you guys can just type it out in the regular chat so everyone could see. Someone sent me a direct message. We got a couple of mixed answers. Let's go over it. Pi bond, pi bond, pi bond. So this is all p orbitals. Hopefully you're not seeing that. Fortunately, we have an sp3, right? Because we have that sp3 carbon. Forget about rule 1. It doesn't fit rule 1. It's automatically non-aromatic. Okay. Now, next one, right? Which one is it going to be? Now, what did I just remember about carbon ions? The lone pair, right? Carbon ions are the only ones that can't rehybridize, right? The carbon ions, right? The lone pair is in a p orbital, right? Only heterocycles like nitrogen, oxygen, and sulfur can rehybridize. Carbons, whether they're carbocations or carbon ions, they're not going to be able to change their hybridization. Which should give you the answer is anti-aromatic, right? We have 1, 2, 3, 6 electrons from pi bonds, right? We have 2 from the lone pair. Negative charge is just meaning one lone pair there. That's showing the carbon ion, right? And if you want to see why the structure is like that, so if we drew this out, right, this is a hydrogen that's not shown, right? So this negative charge or the lone pair, right, has to be in a p orbital, right? So that's why carbon ions are locked into that kind of positioning there, right? I mean, technically they have 4 electron domains, right? But that last electron pair, right, is in a p orbital, right? It can't switch out of it, right? That's the only place it can be in, right? So this one is anti-aromatic. Move this down below. So, okay. So that was B. Okay, what about C? Oh, we did do C. I just realized we did that one. Forgot what that's called. I want to say like a Zeradine or something. The nitrogens always have funny names. It's probably a name for that hydrocycle. I just don't remember it. But yeah, it's going to be aromatic, right? There's two lone pairs here, but all the pi bonds are in the ring, right? P orbitals are all in use. There's 6 pi electrons, right? It's going to be aromatic, right? D, those two lone pairs, right, are not part of the thing, Madrona. The two lone pairs, right? The electrons are not participating in aromaticity since the p orbitals are being used. Okay, so yeah, D. Okay. So we are saying anti, D is aromatic. Okay, so we have quick. So this is what's called a PAH, right? I think this is azulene. Pretty sure. Not Decalin. Yeah, I think this is azulene. So anyways, PAHs, right? Polycyclic aromatic hydrocarbons, right? The way the way you're supposed to do it, you don't count all the electrons. You check each ring to see if it's aromatic. I mean, technically, you could also, do it together, right? In the sense that, like, the rings are like this is all one giant compound. But what you're supposed to do is just independently check each ring, right? So here, right? What is it? How would I do it? Essentially, you could make this one part of the ring, right? So this would be a p orbital, and then positive. The electrons would be here, and this would be here, and then you could say, actually, let's fuse this a little better. Yeah, so this would be positive. This would be where the lone pair is. Same thing here. This is negative, and this is positive, right? So here, right? If you look at it, you have 2, 4, then this lone pair, a positive charge here and a positive charge here. So these are empty p orbitals, right? This is a filled p orbital, right? And there's 2 and 2 here. So in this specific ring, this side here, you have 6 pi electrons and it's planar, right? So that's aromatic. Oh, wait, I did this one wrong. Sorry about that. It should be negative here then, positive here. 1, 2, 3, 4. Yeah. Okay. It's still
Wait, Drew,
filled.
can you explain why D is aromatic? I didn't understand.
Let me draw it out a little better so we have more space to do it. Now we could do it the other way, but you're not supposed to do it that way, as far as I know. 1 second. Let's make sure I draw it. So 1, 2, 3, 4, 5, 6, 7. Okay. Now if we split up these molecules, this pi bond will stay the same, right? This pi bond, right? We could break it so that the lone pair is here, right? P orbital. This is going to be the positive charge, empty p orbital. You have pi bonds here and here still intact, right? And then we could break it this way too, where second, making sure. Yeah, so that should be 6. Hold up. Give me a second. Yeah, I think, okay, so you can only break one bond. Sorry, you don't have to break the other bond. Okay. And then that would fill the criteria for both. Okay, so forget the other bond and the other one. Okay, now this should hopefully be explaining it a little better. And we have a positive charge here, right? So if we broke this bottom bond here, let me just erase all this, right? So essentially we broke only this bond, right? Then on one side of the molecule, we essentially have something that looks like this, right? Right, this is cyclopentadienyl carbo. I mean, you could, it's not, you're generally not supposed to, because the Huckel rules and all that, it really only applies to single ring structures. Technically, yeah, if you did the whole ring, right, it's 10 pi electrons, it's aromatic, right? But generally you should do it individually, right? So same thing, right, is if you have the electron on that carbon, right, you have 6 pi electrons in one side of the ring, and then the other 7-membered side, same thing, right? You could have the electrons here, right? This was a pi bond, we said. This was a pi bond. Oh, wait, no. Where's the pi bonds? So here, right, there was a p orbital in use there from the other one. Where am I missing my pi bond? Here probably, right? And this would be positive. Yep. So then it would be 6 here as well. Yeah, I'll have to confirm that with Professor Bisco if I broke it correctly. But then this would also have 6 pi electrons. Yeah, I'm gonna have to double check that. But if you do it the other method, right, then we could just say this is all one gigantic structure, right, that has 5 pi bonds, right? So 5 pi bonds is total of 10 electrons, right? It is all cyclic and planar, right? Even though it's bicyclic or a fused ring, and it's aromatic. I have to see, so ignore this part I did here. I'll have to check with Professor Bisco or Boson if I broke those off correctly, because I might have not. But for now, I guess do it the technically not proper way, which is just looking at it as a whole. So if you look at it as a whole, you'd get the right answer, right? It's just that generally you shouldn't. I mean, because it's, I don't know, PAHs are different. That's why. I mean, the book explains it a little better because like the system was designed for single rings, right? Okay, and then the last one, right? Same thing here, right? Is we have I guess you could consider this a shared bond here, right? So p orbital, right? You look at these individually, right? They all have 2 electrons on each side. This is a sulfur atom, right? Is it going to hybridize sp2 or sp3 for each ring? sp2, right? So then one is in a lone pair. I mean, one is in a p orbital, one is in a p orbital there, right? So then if you look at each ring has 6 pi electrons. If you looked at it the whole way, like you said, the whole way does work. And I used to always do that before. And then I forgot who it was who told me that you shouldn't do it that way because the rules aren't designed for that. I used to always do it like for fused rings for just, I was just like, oh, you got, 6 electrons, why not? Yeah, I always did get the right answer, but it's just like, I was just told not to do that. That's why I stopped doing it. So if you looked at it the whole way, the same thing works. It has 2, 4, 6, and then it has lone pairs. If you made both of these sp2, only one lone pair gets in. That would make it 10 there as well too. So individually, each has 6, right? And as a whole, it has 10, right? So it is also aromatic. Yeah, I know you have a valid shortcut. It works, but yeah, that's why I try to make sure we do things properly here. Hey, you're right. If it works, it works. Okay, the next question is acidity. And then I'll do one dipole question. So the acidity question brings into Ario stuff. We didn't do too much of the acidity, but if you would, let me check in your textbook. Let me post this actually. And then in your textbook, I'll point out which problems to do that are similar to this exam one. So you guys can start working on that. So rank the following compounds, their acidity. So 1 is the most, 3 is the least acidic. Think about Ario factors here, right? Right. Except now, in addition to the Ario stuff, aromaticity comes into play, right? So that's the hint I'll give you there. Let me find the examples in your book that do yeah, you see, okay, I'm scrolling through the chapter, polycyclic aromatic compounds, or PAHs, right? Huckel's rule is meant to be applied for a single ring, right? Are known to be stable and have, like you have naphthalene, anthracene, and naphthalene we use a lot in our lab. But yeah, see, you're not supposed to, but hey man, if it works, it works. But I think that the way I broke it down should be, for the second one, I know I did it correctly. For the first one, I have to double check. But okay, so yeah, just work on that problem. Let me just find the acidity questions for you guys. Oh, damn, I just realized. Well, we'll do that in with chapter 18. That's I usually like doing the benzylic reactions when we do all aromatic reactions. So don't worry, I will cover that next week. Where is the acidity questions, man? I guess this doesn't have it. Oh, okay, here we have a couple of different examples here. Okay. So you have 17. So I'm gonna write it above. So 17.37, 17.39, right? What else? Did he do frost circles? I forget. I don't know. I don't think that's usually covered in thing. I mean, I know the book has an example of frost circles for like aromatic. Like, so that's a way to do the molecular orbitals for aromatic stuff, but I don't, I would assume he probably showed you guys a frost circle, did he? Or if he didn't, then don't worry about it. Have you guys heard that term, frost circle? I just saw a question about that. Well, we'll take the silence as a no. So 17.3739, do the acidity. Yeah. And then obviously all the other problems he suggested in the syllabus for you to review. And I think boson also has problems he to ask you to review. But those are acidity-based questions. And we'll do one more, which is the dipole question. Right. So it's not really asking you for aromaticity or not. It's asking you to rank the acidity, right? Which we do by analyzing the conjugate base, right? And in this case, we look, let's see what happens when we do that, right? So in the first one, let's pick off one of the hydrogens. We make our conjugate base here. Right, so then we'd have negative charge here, pi bonds here, right? In the second one, let's pick off a hydrogen. We have the cyclopentadienyl carb anion, right? So negative charge there. And then the last one, right? We could just pick off one of the hydrogens from so this would be, I guess, just a carb anion like this, right? Yeah, that should be it. Yeah, okay. So those are all the conjugate bases, right? So first one, right? Let's look at the bases themselves, right? So they're all on what kind of atom? Carbon, right? So in terms of atom, they're the same. They all have resonance structures, right? If you think about them, right? They could all resonate with those pi bonds. Induction doesn't really matter. And orbitals, they're all in, you know, sp2 orbitals, right? So how we do this is based off aromaticity now, right? Is if we look at the first one, we have a carbon ion, so we know this is in a p orbital. We have 2, 4, 6, 8. We know it fits rule 1, therefore it's what? Anti. Good, right? Second one, 2, 4, 6. So let me just write 8 E minus, 6 E minus, right? It is what? Aromatic. And then the last one, it's not even a chain, it's an aliphatic carbon, right? It's going to be non-aromatic, right? So essentially, when we deprotonate the original compounds, right? Because we're ranking the acidities of the original compounds, right? We are going for the first one, A, right? B and C, right? For A, we're going from something just, non-aromatic, right, to something that's anti. So are we going down in energy or are we going up in energy? Right? Are we making this stable or less stable? It's less stable, right? This is not what you want. You want your conjugate. Remember the whole thing with Ario and qualitative analysis is you want your conjugate bases stabilized, right? The more stable your conjugate base, right? This is how we do acidity. The more stable your conjugate base, the more acidic the original compound, right? Because things want to lose protons if they're going to become less, if they're going to become more stable, right? So conjugate bases, you want to maximize stability. That's the whole point of Ario, right? So in this case, we're going from something non to anti, right? So the conjugate base is very unstable. So essentially, this never really wants to lose its proton, right? And now if we compare it to like the last one, or let's compare it to the second one, like B, right? This is non-aromatic right now, right? And it's going to an aromatic, right? So when we remove the proton, right, we're making this a lot more stabilized, right? It's getting lower in energy because it's aromatic stabilized now, right? So this conjugate base, right, is going to be more stable, less stable, right? And then the last one, right? So this one, right, we could automatically put as 1, right? Because right now, right, we are going from non to aromatic, right? So this original compound, cyclopentadiene, wants to lose its proton, so it becomes aromatic and the conjugate base is nice and stabilized, right? And then it's really a matter of C and A, which are going to be 2 or 3, right? C will be more, right? Because it just went from non to non-aromatic, right? It's not really changing its energy levels. If you deprotonated this, it's not making it more unstable than the other, right? Because we know this can just resonate with this and, it's going to be similar to the other one, right? So this would be 2 and this would be 3, right? So once again, to clarify, acidic compounds, things that with acidic hydrogens, right, want to lose their protons to become more stable. The conjugate base, the way we assess them is the stability of the conjugate base. The more stable your conjugate base, the more acidic the original compound. So in this case is here, right? The most stable conjugate base was the one that's aromatic stabilized, which means its original compound is the most acidic one, right? And then the resulting two, right, has to deal with anti versus non, right? In C, it stays non-aromatic in both cases, right? But in A, if we deprotonated it, right, it becomes super unstable, super reactive, right? And just not like probably a very strong base. It's going to be a very unstable base, right? So between A and C, C is more likely to lose its proton because it's not really changing its energy level too much, right? But if A loses its proton, you're going to make it much, much more unstable and reactive, right? So that's why the first B, I guess you could rank this as the one, as the most acidic, because its conjugate base is the most stable. C would be the second one because it's more stable, the conjugate base, than the first one, which will be 3, right? So if you get an acidity question related to aromaticity, you look at the original compound, seeing if it was non-aromatic or aromatic or anti or whatever it might have been, and are you changing it to something more stable or less stable, right? And that's how we got the rankings, right? And the last question, which we will leave off on, is the dipole question. Where is that? Question 6. So sometimes he might ask this. Wait, no, sorry, question 5 here. Oh, it doesn't really fall below it. If anything, I'd probably put it above. It's more that all the other Ario factors are very similar in this question, right? Because everything here, right, is a carbon, it has resonance structures, inductive effects are the same, and orbitals are the same. But I would probably honestly, like, it's something you have to do in addition with Ario, right? Because what if one of these was an oxygen, right? That was, and like it was, or a nitrogen, right? Then the one with the nitrogen automatically will be more acidic than the other ones, right? So it goes in hand with Ario, right? It's just one additional thing you have to look for now. Okay, same as cardio. I like that. I don't know if this is a joke for cardio or if it's an actual thing, but I would assume you're just joking. Okay, let me post the last one. And oh, okay. Oh, sorry, I didn't show you guys. Yeah, this was the fun from before. Now I realized what I did wrong. Okay, yeah, I completely understand what I did wrong now. In terms of the structures independently, I had to do 2 arrows actually. So you know what? We'll do this one together actually. So the second one, you guys, I'll give you 2 or 3 minutes to try on your own. So then you get an idea of what it is. Because quickly looked at it and then I realized, okay, now I see why I messed up the resonance structure in that first question. Okay, 1 second. Ugh. Okay, 7-membered. Okay. Yeah. Okay. So it says each of the following compound has a large dipole. Draw a resonance form for each compound that explains the origin of this dipole, right? So what I did originally was I tried to flip 2 bonds into plus and minus orbitals, but really, like in the sulfur question where they were sharing 1 bond, right? That's originally what I was trying to do, but I just messed up. So what we do, right, is if you resonated this before, right? Now we are doing it properly, right? This is going to go here, right? And this is going to go here, right? So if we did a resonance structure like that, like if we move those 2 bonds, right? Essentially we'll get same thing. negative here. So this is what I was trying to do, is get the bond over here, right? I'll actually draw this bond like this, right? So it looks like it's kind of shared between them, and then here and here, right? So then this is the positive orbital. Yep, that's what I was trying to do, right? This is the filled p orbital, and this is a double bond, right? So the kind of logic behind this question, and it'll help you answer the second one here, right? Is now if you look at them independently. So yeah, this is what I was trying to do with that first ring. That's why it was easier for the second one, because it was already kind of lined up, right? Is why it has a dipole is because now independently, right? If we broke these rings apart, right? This is what I was trying to do, right? This is the cyclopentadienyl, right? So that's aromatic stabilized, right? And then this is the heptadienyl carb cation, right? So this was a 7-membered ring, right, with a positive charge. So these both have 6 pi electrons. They're both planar and they're both aromatic. So when it resonates like that, or really if you see this molecule in nature, you'll see that the small 5-membered side of the ring is more negative, right? So here, let me just write that down. So this would be negative. I'll write negative. Because if you push this electrons this way, right, it makes a aromatic 5-membered ring, and then this losing its electrons would make a aromatic 7-membered ring. So this side would be positive, right? So all you would have to show, and if you get a dipole question like this, is try to break the rings or the molecule in a way that essentially makes both sides of both rings individually aromatic, which was, I was trying to do that first in this question here, and I just completely botched it. But funny enough, this is on the same exam. So if you got this right on the first part, you would probably get the answer to the second, right? Yeah, so you want to make it shared. So that way, because remember in the sulfur one, I considered the thing shared because it was already in that position. So I just broke them individually as sharing that pi bond, right? That's the exact same thing you're trying to do here. But I just messed up the first time because I was trying to do 2 pi bonds. It still ended up working, but it was the wrong explanation. But this is the better explanation of why individually each ring is aromatic, which makes the entire molecule aromatic. But the question asked why it has a dipole, right? And the resonance forms show you that, because when it has its resonance form here, right, you can see that each ring is aromatic. So your answer would be each ring is aromatic. Therefore, larger ring is positive, and the smaller ring is negative, right? And that creates a dipole, right? Because essentially you could say this is going to be partially negative, this is going to be partially positive. Yeah. Yeah, I mean, the entire compound itself is aromatic. This question is more asking why one side has more electron density and why one has less electron density. And that has to do with if you individually broke them apart, you would see that one ring is a positive aromatic ring and one ring is a negative aromatic ring. But the entire molecule is automatically aromatic, as we did earlier, right? This is more to show why there's a dipole in the moment. And the dipole exists because of the individual rings. One is a aromatic ring with a positive charge. One's an aromatic ring with a negative charge, right? So now you can use that same logic to do the second one. So I'll give you guys a minute or two to do that. Use the same thing. Try to break a bond in that molecule, which is kind of an obvious one, and make each thing independently aromatic. This second one is a lot easier to do. I'll give everyone like a minute to do that, or 2 minutes, then we'll go over it. Well, the first one, right? Because there's no charges, right? Remember, the most significant structure, right, is minimizing formal charges. right? The resonance structure just, in this case, the resonance structure is just showing where you would expect to find electron density, right? That's what I always like. I was just talking to this about for the Orgo 1 class. All resonance structures don't exist in real life, right? They're just a way for chemists to have an idea, like a qualitative idea of where we expect to find electron density and where we don't. So in this specific molecule, right, we're gonna see it has a resonance formula that looks like this. So we'll see the 5-membered ring is more electron rich and the 7-membered ring is more electron poor, right? Because individually they'd be aromatic that way. But in terms of total structure, the first structure is the most. Well, I mean, yeah, it doesn't physically exist, but it drives a lot of the reasoning why things act the way they do, right? It's instead of putting, I mean, that's what computational chemists do, is they put this into numbers, which is still taking them a long time. But like we try to qualitatively do this. Yeah, but I can see how it could be annoying. I don't blame a lot of people because there's a lot of, it's not like hard math like Gen Chem or Go, right? There's a lot of logic and understanding things, you know, how they move around to become, you know, more stable or whatever. But I always say organic chemistry is literally just follow the electrons wherever. That's all you're doing. It's just the movement of electrons in all these hydrocarbons, right? Okay. So Mohammed there said left ring would be negative and the right ring would be positive, and that is correct. So let's draw it out. So if we did this, we had this, right? And we had the 2 bonds here. So if we moved, so let's do it both ways just to make sure we don't mess up here. If we move this way, right? We'd have a resonance structure that looks like, so always go both ways or like multiple ways if you, just to make sure. Right? So then this would be lone pair negative, this would be positive, right? So if we do it in this orange route, right, essentially we have 4 electrons here, and we have 4 electrons here. So each of these rings are what? Anti, right? Not good, right? So it wouldn't ever resonate that way because it's making it more unstable. Now, if we went the blue pathway, right, where the pi bond went and its lone pair ended up there, then we'd get a structure that looks like positive, negative, right? So now we have 6 electrons here, right? 2 from the pi bonds, 1 from the lone pair. We have 2 electrons here, right? And these are each aromatic, right? They're planar. They have the p orbitals all overlapping, right? 2 electrons, right? Just to be clear, this fits for 4n plus 2, n equals 0, right? It's gonna be 0 plus 2. So this is also aromatic, and this is also aromatic, right? And that would essentially give this a partial negative charge. Or I guess you could say full positive or negative, and this would be partially positive. So you would show, if you want to also show a dipole arrow, the dipole arrow would be going like that. And then for the first one, the dipole arrow, right, would be going this way, right? So yeah, that should cover everything in terms of this pure aromaticity. How to, you know, check for hybridization states, the criteria, you know, labeling them, dipole moments, and acidity. We're gonna end off here. Next week, I will do some of the reactions from this chapter when we go over all aromatic reactions. I have to figure out when we can do that exam review. Maybe Sunday night. Because I don't think Monday night will be good. Because I usually come back from the lab late at night. Sunday night most likely is if I do it, I will do it then. What is the exam on? That's up to chapter 18.
I think he said it's on ethers epoxides reactions, chapter 17, which is everything of aromaticity, and I think he's doing Diels alder reactions as well, and the orbitals that we went over.
Okay, no, it's also gonna be NMR. Okay, so 13, 16, 17, 18. Okay, so 13, 15, 16, 18, and sorry, 17 and 18. He said
What is
no
the-
NMR?
Yeah, he didn't say anything about NMR.
Because on your syllabus, I just pulled it up. It says a review of aromatic compounds, NMR spectroscopy and review. So, I mean, you'll find out next week if he goes over NMR or not. But anyways, yeah, so it'll just be like 3-4 chapters. And what is it? 16, 17, and 18. Oh, sorry, and 13. So 13, 16, 17, 18 may or may not have 15 in it. Because he'll miss a class, but won't be. Okay, so he said, okay, so don't worry about NMR then right now. Okay. Oh, he said no class. Okay, gotcha. All right. Okay, so I'll end the recording.